what I expect from you guys. Next week, next Friday, we'll start beam deflection, and then the week after that, you guys will be back in lab. So today I'm going to go over hardness and fatigue. There's no questions. All right, so again, hardness and fatigue. You have hardness. That's pretty much how hard a material is, how much you can indent it. And fatigue is how much stress the material can take over time, cyclic stress, before it fractures. So the whole point of this is we want to make this diagram right here. We have hardness Brinell's number versus the specimen ID. If you guys remember, there is an equation. It's an empirical equation. So you need to use these exact units in it, millimeters and kilogram force. I remember going over kilogram force last week, but that is not kilograms. It takes, or when kilograms are in 1 kilogram force, it's like the same as pound force. And then we also have fatigue. So we were going to make this graph. It's called an SN diagram. So you have your stress range, which stands for S, and then your number of cycles, which stands for N. So we're going to go ahead and plot that. We're going to create a logarithmic scale down here, and I'm going to show you how to do that in Excel. And then what we're going to do is we're going to create this lower bound. So we have our data, we have our trend line, we have the equation for our trend line, and then we're going to create this lower bound. And that's the lower bound you'll actually use to design with. So any questions on hardness and fatigue, I'm just going to hop into the Excel. There's a lot of Excel work, so if you do have a computer, I recommend you follow along if you can. Okay, so the way this lab is going to work, you're given data, and you're going to be able to find it. For activities. So then here's the hardness data. You can just download the Excel file, and then here is the fatigue data. I already did that. So once you download the file, you get this macro, and you just push this button right here. It's going to generate indent diameters based on force and specimen ID. So this actually doesn't work on any of the computers here at school. Like the school locked. So I think we created this macro, and the school doesn't trust it, so they don't let you use it on the computers. So if you guys can't get your data to be loaded in, send me an email, and I will load it in for you. But I recommend trying to get it on your personal computer first, because I just don't think any of the engineering computers can have it. But yeah, if you can't get your data to load, if this button doesn't work for you, send me an email, I'll load it for you, but don't send it the night the report's due, because then I'm not going to get back to you, probably. So definitely start the report a couple days early to make sure you can actually get the data with your computer. If you can't get it with your computer, what you do is you go to options, and then you go to trust center. Yeah, you go to the trust center, you go to trust center settings, and you have macro settings. So on all the engineering computers, you can't change this. You have to have admin access, and you need a password for admin access. So you can't really change it. But on your personal computers, you should be able to change this. So if the macro is not working, go here and click Enable All Macros. It's not recommended because you can get a virus. So if you do get a virus, don't blame me. But that's what you got to do to get it to work on your personal computer. Anyways, any questions on the macro and how to get it? You can always look it up, how to enable a macro. You can look it up on Google. Hopefully, I'll with that. Anyways, I loaded my data in already. So I'm going to start with hardness. So I went ahead and created a new Excel file because you don't want to modify your raw data. So what we need to do is we need to calculate the Brinell hardness based on the inlet diameter using this equation. And then what we need to do is we need to flip it so we can graph it. Anyways, I'm going to go ahead and calculate it really quick, and then I'm going to flip it. So we have, and we're given force, right? So this equation only accepts kilogram force, not newtons. We need to change 5,000 newtons to a kilogram force. And to do that, you divide by 9.8, divided by gravity. So we got our force in there now. Multiply that by 2. We're going to divide by pi times our diameter. So this diameter, the capital D, that is the diameter of your indenter, which in this case is a tungsten ball, tungsten carbide. And it's given right here as 10 millimeters. Multiply that by 10 millimeters. Yeah.
What's the question mark for?
Where do you see your question mark?
In your equation, you have 2 times your C5, 9.1.
Oh, that's a typo.
Okay.
I could probably zoom in for you guys too. Okay, so equals 5. Oh, I don't know why I'm putting units in there. 10. 10 minus the square root of 10 squared minus our indent diameter, that's the lowercase d, and that is cell B5. I can't click it right now. Square that. Over the parentheses. Yeah, I believe that's all we gotta do. That looks right. Okay. Any questions? We're just using the equation right now and the given data. Okay, so a little trick you guys can do. You can literally just take this, control copy it, paste it, and it will just move that equation over. Save you a bit of time, hopefully. So paste this equation over, make sure it's grabbing the right stuff. It looks like it is. Do that for all 4 specimens. Okay. Now we just calculate the Brinell hardness. Now we need to graph it. So before we can graph it, we need to turn each one of these sideways. That way it can be put into a bar graph. So that's going to take a couple steps. So the first step I'm going to do is I'm going to change this from an equation to a number. I'm going to move it over here, paste it, and I just want to paste the values, right? So I'm just going to move it over and paste just the values, not the equation. Yeah.
What are you clicking to make it just the values?
So once you control V, there's this little control thing down here. So you click that, and then there's paste values here, so you just do values. Yep. this is actually kind of agonizing doing the hardness. It just takes forever. Okay. So we got our values. So now we're not dealing with equations anymore. So now we can actually flip it. Because if you guys see, if we try to flip this here, I'm going to copy it. Go over here. I'm going to paste it. And then to flip it, you do what's called transpose. You click transpose. But like, it doesn't do anything for you because like you can't really flip it until you change it to a number. That's why we did that. What we're going to do is we're going to go ahead and transpose all of these one by one. It's really painful. But again, that transpose thing is once you paste it, there's this little control box down here. You do that and transpose. Boom. It just flipped it over like that. And then you gotta do that for each and every one of these. Just sit tight while I do this really quick. Oops.
There's no like hotkey to paste this transpose?
I think there is a hotkey. It's T. Yeah. Other than that, yeah. I mean, if you guys can find a better way to do this, I would love to hear about it. Because this gets annoying. Okay. Yeah, that's a pretty slow process. But anyways, we got all our things oriented correctly, all our values, so we can create a bar chart. I'm just gonna clean it up a bit real quick. There we go. So everything we need to create a bar chart. What we're gonna do is we're gonna select these numbers here. We're going to go to inserts, and they call it a column chart. Essentially, we're just going to insert a clustered column. Then we need to change our horizontal axis. Our horizontal axis are going to be our specimen IDs. Then we need to change these names. So series 1 is going to be 510 kilogram force. 2, 1530 kilogram force. And that's it. So you guys can see, now create a bar chart. We have our steel specimens here, our annealed steel specimens here, our brass specimens here, and our aluminum specimens here. You can see when you put 510 kilogram force, it kind of has a little bit higher. Actually, it should normalize. It should be about the same. It doesn't really matter what force you have. You're going to get the same hardness number. So anyways, you should have 3 different hardness numbers for each sample based on the loading. And then you create this chart. Any questions in creating this? I'm going to move on to the fatigue calculation. Again, this is in a different Excel file. So pretty much, you have this, you push the button if the Excel macro works, and then you create a new file or a new sheet, so you're not messing with your raw data. So I literally just copied it over to a new sheet, and then what you do is you go ahead and do these calculations. So you're going to find the stress range or the amplitude. We call it SE prime. That's our stress. And you find the moment of inertia from a circular section. So really quick, I believe the video I showed you guys last time was they had an axial apparatus. It applied axial loading to the specimen. So tension, compression over and over again for hundreds of thousands of cycles. There's another way to do it is where you use moment. So you apply a moment and then you can back calculate the stress cycles, the axial stress in that moment. So that's the way we're going to do it. So what we need to do is we need to use some different equations than you used to. So this stress is not force over area this time. It's moment times radius over the moment of inertia. The stress is normally force over area, but since we're given a moment, we need to do a different equation. These equations and the way I set up these tables are available in the PowerPoints. This one. So this table was the one we just did. And then these tables are the one I have now. So you have the fatigue table set up and the fatigue lower bounds. That's these right here. These equations are also in here somewhere. Right here. These equations are right here on this PowerPoint. Yeah. Anyways, what we're gonna do is I'm just gonna go over a Neil Still calculation for Neil Still with you guys real quick. Copy this over. I just want the values. Cool. Radius. That's half of your diameter. Moment of inertia given right here. That's going to be pi divided by 64 times our diameter to the fourth. Let's see. Yeah. Okay, then our SE prime. I guess you can put a prime there. For SE prime, going to be our moment. That's in inches and pounds for us. So we make sure our units are staying constant here. So our moment multiplied by our radius. That's in inches too. Good there. Divided by our I, which is also in inches. So we're good there. Boom. However, you guys will notice the units here are KSI. And this is in PSI right now. So I need to get this to PSI, or I need to get this to KSI, right? Because I calculate everything in pounds and inches, so it should be in PSI, pounds per square inch. So I need to get to KIPS. That's the easiest way to do that. Divide everything by 1,000. Cool. So now we got our stress range in KSI. And then you're going to do that for the next 3 specimens: steel, brass, and aluminum. Now, if you remember from the last Excel, what we just did a few moments ago, you can just copy and paste these formulas over, right? And then you need to, actually, before you do that, you don't want to copy and paste that over. You bring in your data first. Then you copy and paste the actual formulas. There you go. Make sure that it's grabbing the right data. It is. And then you can bring that down. And then fill in the rest of the tables. But I'm going to go ahead and make the SN graph, the SN diagram for this now. So that's going to be a scatter plot. going to be a scatter plot. It's going to be your number of cycles on the x-axis. Really quick, let's just call this yield steel. And each specimen or each material is going to have their own graph. We're going to grab our cycles and our stresses. My graph's in the way. There we go. All right. Steel. X. Y. Okay. So now, we got our graph. So you guys can see the discrepancy here. All of our data is kind of scrunched up here because once you get to a certain number of cycles, it really just moves everything back. So you can't actually tell what's going on here. I mean, what you can get from this is you can see it kind of comes down and then it flattens out as you get over here. So if you guys remember, that's the fatigue limit. So you can kind of get the fatigue limit from this. But what we really want is we want to see what's in here in this jumbled up data. So what we're going to do is we're going to create a logarithmic scale on our x-axis. So I'm going to do that by double clicking the x-axis. And there's this little button here. It says logarithmic scale. You're going to check that box. And you can change the base if you want to, but 10 is what I want you guys to have. So I guess you can't change the base, but if in other classes, I guess you can. But 10 is typical. Then really quick, I'm going to paint my bounds because all this is kind of useless to me. There's nothing there. So I'm going to make the minimum 1,000. There we go. Now what I want to do is I want to add take marks. So you guys don't have to do this. I just kind of like doing it because it's a logarithmic scale. It rises to a logarithmic scale. So what you do is you go to take marks, you go to minor type, and you do cross. So you can see it creates these crosses down here. So it goes 1,000, and then what's that? 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. You guys don't have to do that. I just think it looks better if you do that. You're going to add in your axes titles. So this is number of cycles. Oops. Cycles. This one is stress. And this has units of KSI. Number of cycles does not have units. So now what we need to do is we need to find how to figure out this lower bound. So generally in design, you don't design based on the best fitted line, because if you design based on the best fitted line, you can get in trouble because look at how many dots are below the best fitted line. So you create a lower bound and you design based off that lower bound. So if we're going to do that, we need to find this equation. The equation will align to the best fit. And then we can use that equation to create this. Let's do that. Add a line, trend line. So this line is actually straight. It doesn't look straight, but it is straight. Because it's logarithmic, it doesn't look straight. So what we want to do is we want to make it look straight, but not be straight. So to do that, you create a power curve. So now it's straight. We did that by creating a power curve. So now spinning our data. We need to find out the equation, and then you always generally add in your R. This is like an R of 0.7, so not the greatest R squared value, but it's close enough. You can see it gets us a line. So now we have okay. We're gonna create our lower bounds So you're going to start with 1,000, and I think this is 10 million. So I just recommend using these numbers. These numbers are based off of your stress being in KSI, so you need to make sure your stress is in KSI before using those two numbers. And then you start with this guessed value. So I know it's going to be 32.5, so I already have the guess going. So 32.5 is a good guessing value. Now we need to go ahead and calculate our other point, right? Because to create a line, you need 2 points, one here and one here. And then a line connects the 2 points, so we need to find a point here and a point here. So each point needs an x and a y value. So what we're going to do, we're going to use our equation of best fit. This y equals 59.129. So look for y, so 59.129 times our x. That's our x raised to the negative 0.073. Okay. We're going to go ahead and add that line. We're going to add data, add, we're going to call it our lower bound. Here's our x's, here's our y's. Okay. And then give it a trend line. Make sure the trend line is a power line. There we go. That's how you create that. Now, this looks a little funky. Why does it look weird?
Is it a log line?
Oh, I see. Oh, yeah. Yeah, you're right. Need to add this value. Okay. And this needs to be negative now. Right. So this equation gives us a line that goes up, because as you increase x, it increases. So we want it to follow this, so I'm going to go ahead and give that a negative value in front of the 59 and bring it back down. There we go. So again, to reiterate that, you have this equation, you have your y equals equation. So you're going to use that to find 2 points, technically just the 1 point over there. So you go ahead and use that equation, so 59.129 times x, this is our x, and then you need to add in the previous y as kind of like a y-intercept, because if you guys remember, y equals mx plus b, so that's kind of our plus b right there. And then this is a negative trend line, so you need to add that negative, and that gives you pretty much a parallel line to this. If you just use the equation, I think that's okay. It just ends at the same point, and that's yeah.
What's the 0.073?
So that comes from here, x to the negative
I
0.
see that.
Any other questions?
Is that plus U4 in the exponent or next to the equation?
It's next to the equation, so it'll be more like outside of the equation, I think. Yeah. Okay. Now, there's like 3 different theories on where this line should be. Should it be above the lowest dot? Should it be way below the lowest dot? Like, do we want it to be up here? Maybe we could bring it even closer to the line of best fit. Is that what we want, or do we want it lower? There's 3 different theories. They're based on some complicated statistics. We're not going to go into that in this class. So what I want you guys to do is I just want you guys to aim to get this line where it just barely crosses over 1 dot. And then all the other dots are above it, okay? If you're interested in these theories on how to calculate where that line should be, Send me an email and I'll send you the article that tells you about it, if you're interested. Anyways, that's how you create this graph. Make sure you add a title. Everything. And then you gotta do that 3 more times. Okay? Alright, I'm gonna go over the template really quick. So you're gonna have a graph that looks like this, kind of. It's a little more separated because it's generated in Excel. I don't know where this one's generated from. And then you're gonna have this graph, which is what we just made. And you're gonna have it for the 3 other materials too. And the whole point of this lab is I want you guys to find out if you can use a hardness value to determine fatigue, or if you need hardness to determine stress and strain, ultimate yield, fracture. So what we need to do is we need to create 2 more graphs. I'm not going to create them here, but I'm going to show you guys what they look like. We're going to create 2 more graphs. You can create any 2 graphs you guys want that has to do with fatigue, hardness, or stress and strain. If they don't have anything to do with those 3 things, then you're not really following the directions. So make sure what graphs you're creating have to do with what the lab is about. But you can create any 2 graphs you want. The 2 graphs I created are right here. So what I did was I put all these curves from the fatigue on one graph, and then I averaged the hardness graph. So let me show you guys in Excel. So we have our fatigue and our hardness. Now we need to figure out if we can use these 2 graphs to see if you can predict fatigue from hardness, okay? So let's actually see if we can do that right now. So let's look at steel. So steel is really, really hard, right? It's the hardest